I'm going to talk about category theory and also translating it immediately into Haskell. So if you have your laptops with you, you know, you can do some exercises, okay? Because I want to show you that you actually can take this very abstract language of category theory and treat it just as a tool, you know? Category theory really talks about points and arrows. That's a visual language that we use in category theory. And I want to show you how to take these points and arrows and translate them into actual code. But this is a very restricted language, right? The syntax of this language is very restrictive. So in order to define familiar things in this language, we'll have to do some really crazy things. And I'm going to introduce what is called universal constructions to explain how you can define things just using points and arrows. Just not a trivial thing, okay? So there's a feedback here. Is there? Why is there?
He's taking care of it.
Yeah, okay. So let me draw an arrow, okay? So, yeah, okay. So, and we give names to these things. So this is an arrow that goes from A to B, and we'll call it F. And it immediately translates into Haskell as a function from type A to type B. That's all you need to know as far as the semantics of this goes. Right? What are the things that you can do with arrows? So that's the important thing. Very few things, actually. Right? You can compose arrows. So if you have an arrow from A to B, and you have another arrow that goes from B to C, so the target of one has to be the source of the other, right? Then you can replace it always with a single arrow that goes from A to C. Okay? And this arrow is called the composition of these two arrows. It's written, in math, it's written G after F. That's how we read this. In Haskell, this is simply G dot F. Right? And it just means, you know, well, when the time comes to execute this function, you first provide an argument of type A, execute the function F, it will produce something of type B, well then call the function G with this result, and it will produce a result of type C. So that's totally simple thing, right? The other thing that we can do with arrows is we can compare them for equality. So we can say that, here we just say that this is equal to this. That if you go first F and then G, that's the same as going G after F. This new function that was defined as a composition of the function is actually equal to the composition of functions, right? So these two things, and that's actually enough. Now, they satisfy certain conditions, right? Which are really, like mathematicians say, the obvious conditions, right? What are the obvious conditions? Well, if you have three arrows, okay, you want to be able to compose them, right? Let's say F, G, and H. There are two ways of composing them. Okay, you can first compose G after F, so you get this arrow. Okay, going from here, from let's say A, B, C, and D, right? You get this arrow, and now you have again two arrows that you can compose, right? So you can compose them to get this arrow. Or equivalently, you can compose these two last arrows, H after G, right? So this is H after G. And then now you have two arrows, F and this, and you can compose them, right? And you get H after G composed with F. And this one is H composed with F, G after F. So this is why mathematicians call it obvious, right? I mean, yeah, it's obvious. It means that you can just write things like H after G after F and forget about parentheses, because it's uniquely defined. You can either calculate it like this or like this, you get the same result. The other thing that's important, and this is something that in Haskell is implemented as a major part of the library. In some other languages, it's not that obvious how to define an identity function, right? So identity function is an arrow that goes from an arbitrary object A back to itself, okay? It's called ID. Now, in Haskell, we implement this as ID, going, well, we can actually say for all A, because it's defined for all types. Every type has this arrow, okay? It goes from A to A. And it just doesn't do anything, right? It returns its argument without making any changes. The important thing of identity is that it's an identity with respect to composition. So if you compose, let's say, a function f, and then after you do an identity, it's the same as f, right? Composing with identity doesn't change. So this is the right identity, and this is the left identity. So you first apply identity, and then you apply some function g. It's the same as g. Okay? So far, these are obvious things, right? So with this, with these tools, what can we do with these tools, okay? So the idea is that in category theory...
Do you want to maybe try this? Maybe this is maybe less of a problem for you.
Is this?
Maybe it won't slip.
Was this slipping?
It was slipping. I thought it was annoying you because it was slipping.
Oh.
But if you want, you can.
No.
Okay, yeah, cool. Good.
Okay. But where are the...
I can give you the papers are here.
Yeah, okay. Here's the stash of papers. Okay, so let's think about how is this thing related to programs. So I already told you that arrows will be translated into functions, and these dots correspond to types, okay? But, so we say this is like a categorical semantics of Haskell or some other programming language, right? Like we are mapping everything that the Haskell syntax into things that happen in category theory. So we have this category of types as objects and arrows and functions as arrows. Now, this is sort of a Platonic idea of types. We essentially say we have all possible types in our category. Like, we have natural numbers, we have floating point numbers, we have products, we have sums, we have either, we have lists. All of these things already pre-exist platonically in this category, right? So instead of saying I'm defining what a product means, we might say I'm defining how to find a product in this universe of types. What is the object that corresponds to a product of two types, right? I have two types, A and B. Okay, let me say A and B, right? And I want to define an object that is their product. So in set theory, you would say, you have two sets. It's a set of pairs, okay? What's the problem? But now we don't have sets. We have only arrows at our disposal. So what can we say about the arrows? Well, we can say that if we have a product, let's just write it as A cross B. Okay, here. A cross B, right? So in Haskell, this will correspond to A comma B. Two types A and B. We know that it's equipped with these two arrows, the projections, right? One is called first, and the second is called second, okay? So we could say, okay, we know how to find a product of two things. Just find me an object that has these two arrows, one going to A, one going to B. Now, this is really not enough information, right? I mean, there are a lot of, almost every function, almost every object, every type has an arrow to A and an arrow to B. Like if you replace A with integer and B with, character, right? You can define a lot of objects that have a mapping into an integer and mapping into a character. So this is not enough information. But let me start with something simpler, okay? So we'll get back to product, how to define a product. Let me define first, as an exercise, something that's much simpler. I'm going to define, it's called a terminal object. Okay, to give you the feel for what these universal constructions are. So a terminal object is defined, and in math it's written just as one. Okay, it's an object that has a unique arrow from any other object. Okay, so you have object A, you have object B, you have object C, and so on. Each of them has a unique arrow to this object 1. In Haskell, we call this object unit, okay? This object is a type unit, right? Yes? What's that unique arrow? What does it mean that the arrow is unique? It means that if there is any other arrow from A to 1, then it has to be equal to that arrow. That's the definition, right? So there can be only one. Yes?
Do arrows also have, some sort of identity, some name or something that
Yes.
distinguishes them? Okay.
Yeah, every arrow, we can give names to arrows, and it could be multiple arrows coming from one point. Yeah, this is something that actually may be confusing to a lot of people. You can have different arrows going from between two objects. In fact, you can have even infinitely many arrows going. Each of them is different, right? How do we know that they are different? Because if you compose them with some other arrow, they will give you a different result, maybe, I mean, in general, arrows are not equal. We can demand that two arrows be equal, right? By saying, well, there's a way to get this arrow by composing this thing, right? You can say, okay, I'm getting this arrow by composing these two arrows. But there's another way of composing two different arrows. This is like F prime, and this is some G and G prime, right? I get two different paths. I can say, I demand that these two paths give me the same result. Okay? So we say equality of arrows. So in this case, we are saying if there are multiple paths from A to 1, they are all equal. And we say there is a unique path. Okay, so in Haskell, this as a type, This is called the unit type. And an element, there's only one element in this type, which is also called empty tuple. It's an empty tuple, right? And the function that goes from A. So we'll define this function. It has to go from A to unit, right? We'll call it unit. I think it's actually defined in the library, right? And unit of X equals an empty tuple. Because the unit type has only one element and it's always available. Okay, so this is sort of a trivial thing, right? But it's very important. It's very important that we can define this type, this Haskell type, the unit type, just by talking about arrows. We say, this is a terminal object in our category, meaning there is a unique arrow from any other object in the category. Okay? So that defines, that tells us this is the terminal object, this is the unit type. Okay? Now it doesn't, in category theory, nothing is defined on the nose, meaning you might ask the question, is there only one terminal object or are there multiple terminal objects in a category, right? The answer is there could be multiple terminal objects, but they are all equivalent, which means isomorphic. We'll talk about isomorphisms later. But they are, from all intents and purposes, they are the same thing, okay? So these functions that return unit, in other languages, they just say, well, it's a function that doesn't return anything. Well, it really doesn't, it's not true. It returns the unit, right? In C++, it would be called a function returning void, right? But it's really a unit object, okay? That is always available, and you can always get an element of this unit object anytime. Now, there is one very important, yes?
Define unit in Haskell as from any A to unit. Right. So you've defined all of these arrows with one Haskell function, right?
Yeah, exactly. A polymorphic function, yes.
Related to the fact that there's a unique arrow from every type to unit?
So you're interested in saying, like, how do I prove that this is the only arrow from unit, from X to unit? Is there any other function? So can we think of any other functions that would return a unit from some arbitrary type, right? I mean, of course, I mean, in Haskell we have polymorphic types, so I can use one equation to define all of these arrows, right? A polymorphic function is just infinitely many arrows, right? But it's given by one equation. This is the equation, right? Okay? So I could even write, you know, for all A dot here. Yeah?
So if we wanted the unit arrow for example, dB point, we would specialize the unit function to dB type, right?
Yes, right. So we, if for every concrete type, we just specialize this unit function for this concrete type. We actually don't do it in Haskell because Haskell compiler is smart enough to know what we want, and it will specialize a polymorphic function to the concrete type, depending on the context in which it's used. Like if you give it an integer, well, it knows that it has to go from integer to unit, right? Okay. So this terminal object or unit type has one extremely important property, at least in a sort of Cartesian closed category, mumble. Okay, I don't want to introduce these terms, but it's like it's not true for an arbitrary category. But the one that we are interested in which we are modeling Haskell, it has this property that not only there are arrows going from any object to it, but there are also arrows going from one to almost every type. Well, almost every type that actually has elements. There is one type, the void type, that doesn't have any elements, so there is no arrow going from one to void. But for any other type, there is an arrow from 1 to A. Is it a unique arrow? Not really. Right? I mean, there is a unique arrow going from 1 to 1, and that's called identity, right? But in general, like if you want to go a function from unit to, let's say, int, how many functions like this do we have?
Many as the type int has inhabitants.
Exactly, as many as inhabitants of int. So for every natural number, for every integer, there will be an arrow coming from, and we can implement this, like, let's call this function x, right? And we can give it x of unit equals 42, right? It's a good function, right? But it's not unique. There are many other functions. There's 43 and so on, right? So this arrow serves this purpose of picking elements, okay? An arrow from 1 to any type is called, in category theory, it's called generalized element. But in fact, what we are doing in Haskell, every time I say, well, let's see, let's use an element of this type, secretly, I'm thinking an arrow from the terminal object to this type. Okay? It's just a language. It's just, but it shows you that everything can be done with arrows and dots, right? Because otherwise you would say, well, I know how to, what an element of a natural number is, right? Well, yes, it's an arrow from unit to the object of natural numbers. Okay, so can we, yes? Yes, exactly. So what he's saying is that in category theory, you secretly actually interpret elements as, types as sets by saying, well, instead of saying that it's a set of elements, I'm saying there is a set of arrows that is one-to-one correspondence with elements of this, right? So we are sneaking in the set theory, because category theory depends on sets because arrows form sets. Okay. So can we use the same kind of reasoning to describe products? Okay. So remember, we defined the terminal object or the unit type with respect to all other types in the category. All these, Platonic types that we know exist in the category. We define that using arrows and using this universal construction. Universal construction means that you look at the universe of all possible objects in the category. So let's try to do the same with products. So we know that a product has to satisfy this thing. This is called the sort of introduction of a, no, sorry, this is not an introduction type. This is elimination type. This is the elimination, so as I said, there can be many possible candidates for a product, but there is only one modulo isomorphism that is universal, meaning it can be defined using all possible types in our universe. So let's pick any type C, right? How does this type relate to A cross B? Well, we know that A cross B has these two projections, A and B, right? And we say this object C pretends to be a product. What does it mean? It means that it has two morphism, I will use sometimes the term morphism for an arrow, but it's just how mathematicians call it. So it has an arrow from C to A, let's call it F. Has an arrow from C to B, call it G, right? And it says, well, how do you know I'm not a product? Okay? And you know that this is not a product because for every object with these two projections, there is a unique arrow called H from C to A cross B, which sort of picks the part. So here's the intuition. C sort of contains A and B in it because you can map it into A and B. So secretly contains both A and B, right? What this arrow H, it picks this A and B part inside of C. And this is a unique arrow that makes, and now this is the term that's used all over in category theory, it makes these diagrams commute. What does it mean that it makes these two triangles commute? There is a triangle here, right? And there is a triangle here. Commuting means that the two ways of getting through from C to A are equal, right? We can compare arrows. So how do we write it down? Well, this is first, this is our second, right? So it says that first after H equals F. That's what we mean by it's commuting. It means that these two paths are equal. The first path is a combination of these two, right? And the second path is direct F. And the other triangle says second after H is equal G. Okay? So we sometimes say that there is a unique factorization. It's like if you look at this, if you thought these were just numbers, right? Then we would say that H is a common factor of F and G, right? This is why it's called factorization. That you can factorize H out of F and out of G. So now, what is the definition of a product? The product is an object that has this first and second, an arrow to A and an arrow to B. That's a product of A and B, such that for any other object C that has similar arrows from C to A and from C to B, there is a unique factorizing arrow H. Okay, and you might say, wow, this is like totally an abstract definition which has no use whatsoever in programming. And you'd be wrong, okay? Because now I will actually write some code using this amazing property. Okay, so another way of looking at this property is that I can always replace a pair of arrows from C to A, C to B, right? I can always replace it with a single arrow from C to A cross B. So this is my H, this is my F, this is my G, right? So by universal construction, if you give me F and G of this type, right, from C to A, C to B, there is a unique one, which is called this is called often mapping in. Mapping into the product. Okay, from the object C. But the other way around also works. If you give me an H, right, I can recreate F and G uniquely. Well, F, here it is. F is equal first after H, and G is equal second after H. So it goes both ways, right? These two descriptions are equivalent. Either you give me two functions from C, or you give me one function to the product, right? And in Haskell, so in Haskell you can do this actually, because in Haskell you have higher order functions. So you say, well, is there a function that takes two functions of this type and gives me a single function of this type, right? So this would be a function that goes C to A, right? So now I'm writing code, okay? Watch me. C to B, right? And from this pair of arrows, I'm going to get a function from C to A cross B is just a pair AB, right? Okay. What is this function called? It's actually, there is a function in the library. It's called triple ampersand. Okay? It's in the arrows. It's a control arrow. So if you do exercises with this, you have to include, you have to import control arrow to get access to this, right? So how do we implement this? F triple ampersand G acting on, okay, on some X. It's very simple. It applies F to X and applies G to X. Okay? So that's your translation. This is the universal construction written in Haskell. For any type C, you can do this. It's implemented for any function, for any type C. Give me two functions from C to A and a function from C to A, function from C to B. I'll give you a mapping into the product of AB. Okay? And in particular, you can pick the terminal object for C. Okay? So what does it give you? It gives you arrow from 1 to A, from 1 to B. It's like I'm redrawing this definition here, right? I'm redrawing this definition, but I'm putting 1 instead of C. Okay? This is like all the work that you do in category theory. It's just replacing something with something else. And oh, okay, sorry. Mm-hmm. I want you to see both, okay? Okay, so I'm replacing this with 1, right? A, B. This is my first. This is my second, okay? Now, the mapping from 1 to A, just picks an element of A. This is what we know about terminal object. It's a picking tool, right? So let me call this X. So X is an element of A. Y is an element of B. For any element of A and element of B, there is a unique arrow, H, going from 1 to A cross B. So arrow from 1 to A cross B picks an element of A cross B, right? So what's an element of A cross B? Well, it's equivalent to a pair of elements, one from A, one from B, right? Because X is an element of A, Y is an element of B. I have a pair of elements, right? And it uniquely gives me an element of A cross B. I call this element of A cross B a pair of XY, right? So H is really XY. So it all works, okay? So, do you want to do a very quick exercise? Okay, how about implementing the other mapping? Because this is the mapping, give me two functions, and I'll give you a mapping into a product, right? How about if I have a mapping into a product, can you get me a pair of functions? It's a very simple thing, okay? Yeah, you have your computers? Or you can write it on paper. It's so simple, right?
Isn't the answer on the screen already?
Well, yeah. Essentially. Yeah, you just have to write it in the Haskell way, right? So let's call this function. Okay, I think I'm running out of the black one. Is red one okay? So let's call it this function toProd, right? So what's the interface here? What's the argument? Type of the argument. From C to A comma B, right? This is the product. So this is my H. Okay. And it produces what? Well, let's say a pair of functions, right? So a pair. The first function goes from C to A. The second goes from C to B. Right? So you just read this, right? So you get first dot H, comma, second dot H. Okay? So we have translated this diagram into this function and this function. Okay? Which means that we have the one-to-one correspondence between pairs of functions like this and a mapping into the product. Okay? So this diagram here is actually the introduction of a product. It tells you how to create the product. Given two elements, X and Y, you generate a product. So if you have something defined by using mapping in, then you can always specialize it to the terminal object, and you'll get a way of introducing it, right? Okay, so I think we should take a break now. Okay, I'm getting really slow. Okay, it's always like this. You prepare a lot of material and stuff. Let's take a 15-minute break. Is okay? Yeah. All right. So by the way, this thing here, this is called the introduction. We'll look at the introduction and elimination with other data types as well. So it's good to know that, you introduce a type by saying what are the constructors for this type. So this is essentially the constructor for the pair type, right? And elimination is the other one. Okay. So I want to show you how many different interesting Haskell programs you can write just using this one diagram. Okay. For instance, I want to show you that product is functorial. What does it mean that the product is functorial? It means, well, you create a product from a pair of objects. Object A, object B, A cross B is this new, okay? So we define the action of a functor on this pair of objects, maps pair of object to a new object called the product, okay? Functoriality means that it not only maps pairs of objects, but also maps pairs of functions to a function, okay? So let's see exactly what it means. So we start with a pair of functions, f and g. Okay, I will be reusing these names, f and g, all the time. So we have a function from a to some a prime, and we have another function from b to b prime, okay? We have a pair of functions. Now, product is thought in terms of a functor, okay? Like, you don't really have to know what a functor is, just a mapping of objects and a mapping of arrows, okay? So a functor will map this pair AB into A cross B, into a single object, A cross B. Down? Yes. Sorry. Maybe I should draw a line here. Tells me how to position this thing. Right? Okay. So the pair AB is mapped into A cross B, and pair A prime B prime will be mapped, of course, to A prime cross B prime, product of these two, right? So given a pair of functions f and g, can I find a function that would map their product? Okay. Well, how would I go about doing this? Okay, I want to find a function. So this is how you solve these problems using diagrams. I want to find a function from A cross B to A prime cross B prime. Okay, so let me call this function H. Okay, now I want to fit it into my diagram that defines a product. So, well, I have a product A prime cross B prime. So obviously there is first and second projections to A prime B prime, right? So in order to define this function H, I need a pair of functions that would go here and here, right? Because this is my universal construction. This is the only thing I know. If somebody asks me to define a function h that ends in a product, a mapping into a product, then I say, well, let me use the universal construction, right? A universal construction means I need two functions from my source to A prime and from my source to B prime. Okay? So if you give me these two functions, then I'll give you H. So how do I define function from A cross B to A prime? I have at my disposal these two functions, okay? So I can say, well, let me first apply first. That will extract A from it. And once I have A, I can apply F to get A prime. Okay, so I have a function from the source. So this is what my object C was. I'm just specializing my universal construction because the universal construction says, give me, for any object C that has these two functions, this works. So in particular, hey, let's pick C equal A cross B. Okay, how do I define this one? Well, this one I define by applying first second, right? Apply second, and then follow it with G. And this is a function from C to B prime. Okay? So I can write it as F after first, right? And I have this triple ampersand to combine two functions, right? G after second. So these are the two functions. I'm combining them using an ampersand, and I will get this function H, uniquely defined, right? So I'll call this function BiMap for traditional reasons, okay? And BiMap goes from F, which is A to B, G, which is B, A to A prime, sorry, A to A prime, B to B prime, right? And gives me a function from A cross B to A prime cross B. So I have written, and notice, so this is the important point. When you use category theory, you get point-free code for free. It's like normally you would maybe define it by acting on some arguments and maybe naming the intermediate results and so on. When you just follow the arrows, the result is usually point-free code, because the only things that you have at your disposal is composition, right? So you just use composition of existing functions. And this is a beautiful way of not only writing point-free code, because like a lot of people are afraid of point-free code, because sometimes it's like really difficult to understand. But once you understand how you can do this, you can always take point-free code and draw a diagram, right? And once you draw a diagram, it becomes obvious what's going on, right? You just put the types in between and arrows, and then you get. Okay? So now, this is an example of a more general construction in category theory that has a scary name of adjunction. And adjunction means just that you have corresponding arrows. You have some arrows on one side and you have some arrows on the other side. So we already have this adjunction sort of written down in one way, So it's like, okay, this is like correspondence between arrows that goes both ways. With these two arrows, I get this arrow. With this arrow, I can get this pair of arrows. That's all an adjunction means. It just means mapping of arrows. So this particular adjunction, the one that defines a product, right? This is an adjunction that I can write it. Okay, maybe I use a different color. Let's see, green. So I have a pair of arrows, C to A, C to B, right? F and G. You can give them names, and it means it's equivalent. It means you can go one way or you can go back, right? There are two functions that map this pair to a mapping into a product, A cross B. This is our H. And to go from left to right, what do? We use this triple ampersand that goes from left to right. Give me two functions, I'll give you one, right? And the other way around, we've seen this was this function that we implemented to prod. Now, an adjunction actually means that, there is a one-to-one correspondence. So this is an inverse of this. And you can, in Haskell, you cannot really express this idea other than just using, testing or quick test or something like that. Now, in categorical language, we would say, okay, what's a pair of arrows? Well, a pair of arrows is really one arrow, one thick arrow, in a category called a product category. So if we have our category, let's call it C, right? We can construct from C, we can construct a product category, C cross C, by just saying the objects in this category will be pairs of objects from C. So like A and B, right? That's an object in C cross C. Just a pair of objects, right? A pair of types in Haskell, right? And an arrow in this category, so if we want to go from AB to some CD, two arbitrary objects in this category, well, it's a pair of arrows that goes from A to C and from B to D. So this is this FG, right? So a pair FG is an arrow in the product category. This is an object in the product category. This is an arrow in the product category. So in fact, this adjunction can be said, well, the left-hand side is an arrow in the product category, and the right-hand side is an arrow in our original category, right? Now you can convince yourself that this is a good category because what? It has composition. You can compose pairs of functions by just composing every element of the pair, right? Is there an identity? It's like, okay, so an identity would go from AB to AB, right? And it should be a pair of functions, so you get ID at A and you get ID at B, right? Two identities. Two different identities, right? In Haskell, it's just one polymorphic function for all of them, but, So it is a category. It's called a product category. And this adjunction here goes between two categories. So we have composition, we have identity in this category. Now a product in this language, okay, I should use the product. Product in this language goes from C cross C, so takes an object AB and produces an object A cross B. So it goes from C cross C, from this new category, right, to the category C. So A cross B is just a single object. Yeah? Oh, okay. Do you see colors there? No, not really. That's okay. Okay. And moreover, this cross here, right? It looks like X, but this is a cross. This is the product, right? This product goes from product category to C, and it's also functorial. It means it will also take a pair of arrows into a single arrow, right? Well, this bimap takes a pair of arrows and produces a single arrow, Yes?
So these objects were crossed, the left and the right of this arrow. In which category are these objects?
Here? Yeah, they are in different categories. So this is not an arrow in the sense that we were talking arrow within category, right? This is a functor, which actually is a mapping between categories, right? And we define it this way, okay? So this is a functor. This is why I wanted to show you functoriality, so that you can see that this is actually a mapping from product category to regular category that also maps arrows. The double arrow from here goes into a single arrow here, right? Yes?
So how do adjunctions and functors relate to each other? So every functor is an adjunction, or?
No. I'm just trying to define two functors that will form this pair of adjunctions. Okay, the adjunction. So we also need the so adjunction is defined between a pair of functors that go both ways, right? So this functor goes from the product category to C. We need another functor that goes from C to a product category, C cross C. Okay, so if we give me an object, let's say A, how do I produce a pair of objects? Well, just duplicate them. All right, I can produce a pair A. Okay, I write it horizontally, A. Right? So this mapping from C to C cross C, it's a different mapping. This was the cross, and this is called a delta. It's called a diagonal functor because it sort of produces a diagonal element, right? So this mapping is actually also functorial because you can lift a function if you have a function f from A to A prime. You get also a function from AA to A prime, right? So a function on this side goes into a function on this side. This is delta A, this is delta A prime. Yeah? You see that?
Scroll up.
Oh. Yeah? Makes sense? So you have a function that goes from A to A prime in the category C, an arrow that goes from A to A prime, and you want to get an arrow that goes from delta A to delta A prime, but it's in category C cross C, right? So it goes from the image of delta A to delta A prime. And you do it just by, if this is called F, then you just do it by duplicating F. So both of these things, product and delta, are functors, means they map objects to objects, arrows to arrows. And the fact that they are adjoined to each other means that we can go from, let's say, what was our mapping? If we go from C to A cross B, so that's in category C, right? And in category C cross C, we go from delta C to A, B. So So you have arrows in C, from C to the product. They are in one-to-one correspondence between arrows in C cross C that grows from delta C, which is just duplicated C, into AB. And in category theory, we write this in this very abstract notation. We're saying that delta is the left adjoint of product. Okay? Just if you say that to a category theorist, they will know immediately, oh, that's what you mean. Okay? But these are different ways of saying the same things, okay? I mean, this does not introduce any new information other than a new, more abstract language that can be generalized to other things later, right? But the gist of it is you have arrows here in one-to-one correspondence to arrows here. Yes?
How do I know which adjoint is the left one?
Yeah, that's just what it's called, you know. So because this is on the left, okay, of the arrows, right? So delta C is on the left on the arrow, so it's left adjoint to this, which is on the right of the arrow, right? So this will be on the right, and this will be on the left. Yeah. Exactly, yeah. So delta is left adjoint to cross, and cross is right adjoint to delta. Which is intuitively sort of makes sense because we're talking about left hand and right hand of a person. Right? So, yes?
About the different crosses that were.
There were different crosses, okay?
Well, the question is, are they different? So there's cross in A cross B,
Yeah.
cross in C cross C, and there's the cross in
Oh, yeah, these are different crosses, yeah. This cross, that's a cross of categories, a product of categories. Now, of course, in category theory, all these crosses are really the same thing, right? It's a product, but in a category of categories. That's a product in a category, which can also be defined using universal construction, but in a different category. So yeah, the reuse of symbols in category theory is endemic. Just like in Haskell, yeah.
cross in A cross B, for example.
Yeah, if A and B are objects, then A cross B is just the product. It's actually called Cartesian product. Okay, so if you want to specifically name these things, it's called a Cartesian product. Okay, but if I give you only one example of this thing, then you will say, well, I don't understand the generality of this stuff, right? So I have to give you another example. And another example would be a sum. So since we had a product, we can also have a sum, right? In Haskell, we know what a sum is. It's called either A, B. That's what we call sum. It's a sum type, right? It's a sum of two types. And this is interesting in the sense that the introduction of either A, B, right, or A plus B, I'll call it A plus B to save on paper. The defining thing is that you can create A plus B either by injecting the left one or the right one. So this is called the left constructor, and this constructor is called right. Okay? I mean, in category theory, they have different, like iota or something. But here it's just either A and B is either right? I mean, data. left A or right B, right? So this is the introduction. So this is a very nice introduction. So give me two objects, I'll give you their sum, right? But if you want to define it in a category, then this is definitely not enough. I mean, there are a lot of candidates that have an arrow from A and an arrow from B, right? Which are not really sums, okay? So again, we go this way and we say, but now we are, for some types, we use the mapping out condition. So we'll draw this diagram. Again, left, A plus B, B, and this is right. We say for any, so universal construction, for any other object C, which is equipped with two arrows, so from A to C, and from B to C, right? Let's call it F and G, okay? So I'm repeating the same words, but the arrows go in different directions, right? There is a unique mapping out of a product, H. Okay? So for any pair of arrows, so if C says, you know, hey, I'm actually a product, and you say, no, fake news, because, you know, yes, you have two injections, F and G, right? But I can factorize F and G from the actual sum, right? So we can say, just like we had before, you know, so you have A to C, a pair of arrows, B to C, G. Then obviously you can go, so this universal construction tells you that you can go to H, which is A plus B, to C. So this universal construction gives you, given pair of F and G, gives you an H. And obviously, if you give me an H, I can reproduce F and G. So this goes both ways, right? If you give me an H, then I will say, well, your F is actually H after left, and your G is equal what? H after right. So you see the similarity, right? Now I'm factorizing F and G, but on the left. For the product, I was factorizing on the right. Here I'm factorizing on the left. Okay? So what would be the witness to this? Like from left to right, a function. Can you implement a function that goes from left to right? So it's a function that takes a pair of function A to C, B to C. It's called either, right? Either. So it takes A to C, right? One function. Takes another function, B to C. And it produces a function from A plus B, or either. To C. Right? It's a library function. And it's implemented using pattern matching, right? Or you can implement it, you know, F, G, and here's your sum, you know, and so case analysis corresponds to this. Case S of left A, FA, right B, GB, right? Yeah. But once you have either defined, everything else can be point-free, right? There's not a nice point-free definition of either. At least I don't know. Does anybody know like how to implement point free? No, essentially you have to have some kind of primitive somewhere to do that. So this is called the either function. And of course there is the other way from either, right? From either would go from H to a pair FG, right? Just using this. And this one is point free, right? It's actually H dot left, comma, from either acting on H dot right. So again, okay, so we have a pair of functions here. It's equivalent to a function here, or pair of arrows. This pair of arrows, hey, we recognize this is actually a single arrow in the product category, right? So this is like C cross C, and this is C, and this is a pair of arrows here, which goes. So we have A plus B going to C. That's in category C, and this is equivalent to what? A pair AB going to a pair CC in the product category, right? So CC. And of course, we know that CC is delta acting on C, right? So we have on this side a mapping out from plus, and on this side we have a mapping into delta. So delta will be now the right adjoint of plus, okay? So delta is the right adjoint of plus, and previously we know that delta is the left adjoint of product. So in category theory, you just say that and they understand what you mean. This is one very simple. And so this defines, like the basic algebraic data types, right? Sums and products. You can combine them and using these constructions, the universal constructions, you can show like a lot of properties. For instance, you can show that A plus B is equivalent to B plus A, or A times B is equivalent to B times A. A times 1 is equivalent to A, all using these diagrams. You just plug into these diagrams and you look like what is my C? Let's pick something for C. Can I find these two functions? If I can find these two functions, I'm done. Okay. So we're done with this. Okay, so I want to. I don't know if you do you want to do some coding? So I want to show distributivity. Okay, question?
Yeah, I have a question. Limit construction.
Yes, product is a limit. Sum is a co-limit. Yeah.
Is there an easy way to see a diagram and decide whether I will have
Is there an easy way to see that? Well, define easy. I mean, not enough time in the to like do it in a few keystrokes. Yeah.
Doesn't it just depend on whether you have arrows coming into or out of an object? Because like with the limit you have a cone, and with the limit you have a co-cone.
Yeah.
Yeah, you have either an apex of your cone or like an endpoint of co-cone, and then.
like a limit is defined by mapping into, and co-limit is defined by mapping out, just like product. And the only difference is that in limit, in co-limit, you also have arrows between the objects that are in your base of the cone or co-cone. Yeah. So this is an exercise. Do you feel like doing this? Distributivity, okay? But only one way. We'll see the other way is kind of harder. How would you prove this? No. By prove, I mean construct an arrow that goes this way. How would you go about this? Huh? But see, here you have both sum and product. So, like, which part would you attack first? Okay. Well, this is too hard for me. No, we have to do it in steps. Okay. Did I write it wrong? Oh, okay. B times A, C times A. I think this is A, right? Sorry. Yeah. Yeah. Okay. So, well, it looks like there are two ways of attacking this problem, right? Using our universal construction. Because we see that the left-hand side is a sum, and the right-hand side is a product on the surface, right? On the surface, this is a sum of things, and it's a product of things, right? So we can either go, we know how to deal with mappings into a product, and we know how to do mappings out of a sum. So either will work, right? So let me draw a diagram, right? So this whole thing I can write as one big diagram, B plus A, times A plus C times A. This, I will call this H, okay? So, and this will be B plus C cross A. Okay, so I can say, well, let me define H as a mapping into a product, right? So I redraw this product diagram, right? So this was like first, and this was second. I'm just using the fact that it's a product, right? So first will produce B plus C, and second will produce A, okay? So in order to find H, I have to provide what? A pair of functions, like this and like this, okay? So, what is?
At the top of this diagram, C times
Yeah. Sorry. I can't even write one letter without making a mistake. Okay, so let's call this. Actually, what I have here is like mapping from a product. Oh, okay. From a sum. Okay. Can we do it as mapping into a product? Should be easy, right? So we need two functions, f and g. So let's look at f. I hope it works. So f is a mapping from B cross A plus C cross A. And if I make a mistake, please correct me, right? To B plus C. B plus C, okay. You know what, yeah? Yeah, but I think this is more complicated than necessary, yes?
Can you just put parentheses on the left, like from parentheses, left parenthesis on the far end of B cross C, and then right before the product, and then prove that B cross C plus C is isomorphic to B plus C?
Okay, I want to make this as simple as possible, okay? So that's the idea. Let me start again. Okay, let me do this as a mapping in out of a sum, because this is the simpler one. I mean, both ways will work, obviously, right? And if I don't make a mistake in rewriting this, we want this H B plus C cross A. I want to show you that this is like totally automatic, right? So it's a mapping from a sum, right? So I have left and right. This is how I construct it. I construct it from B times A and C times A, right? I'm just looking at this as a sum. So a sum has two injections, left and right, right? In order to define H, I will need these two functions. And now this is actually simpler, right? Well, maybe, I don't know. So let's call this F and let's call this G. So I did one step in decomposing my problem, right? I decomposed my problem into the mapping out of a sum, and that means I need to find two functions that are sort of simpler, right? If I have F and G, then H will be equal to either F, A, G. Right? So now let me calculate F and G. Okay, so F goes from B cross A to B plus C cross A. This is F. How do I construct F? Well, this is a mapping into a product. So second gives me A, first gives me B plus C, right? So in order to define F, I need these two functions. Once I have these two functions, I will get an F, right? Using my triple ampersand. This function here, well, that's just second, okay? So I already know what this function is. B cross A to A is second. Now from B cross A to B plus C, let's call this F prime. Okay? And F prime, I can already write it down. F prime is just, what do? From this you can extract B, right? And do left, right? So this F prime is left after first. Yeah? Correct? Okay, the second one is G, from C cross A to B plus C cross A. Okay, now again, this is a mapping into a product. Okay, no problem. So second, first. See, at every step, I'm simplifying my problem. So from C cross A to get A, I just do second. Yeah? And this I will call G prime, right? And I can guess what G prime is.
Can you scroll up a bit?
Oh, sorry. Okay. I know what G prime is. I can extract C from this using first, and then inject it as right. Okay? So I have to combine G prime with second using triple ampersand to get this, to get my G. I have to combine F prime and second using ampersand, triple ampersand to get F, and then I take F and G and I apply either to it. Okay? Piece of cake, right? So H is equal, if I retrace my step, it's either one function. This is left after first, triple ampersand, and second, right? Second, this guy, okay? And G prime, G is right after first, triple ampersand, second. Ta-da! Right? Now, if you've seen code like this somewhere in Haskell, you were just thinking, where are they thinking, right? But it turns out, that if you use universal constructions, this is really pretty straightforward, isn't it? I mean, we were always working with, this is, to define this arrow, I need this pair of arrows. Okay. But these arrows in a pair are simpler already because I have decomposed something. So I can define each of them using another pair of arrows until I get to my primitives, like first and left and second. First, second, left, right, and that's it. So now you can say, okay, this is beautiful code, or you can say this is horrible code, right? I don't know. But what this proves is that you can take all these diagrams, these beautiful diagrams, and you can just translate them into code. And you know how to draw a diagram. If you are to define a function like this, that's either a mapping out of a sum. So this is what you have to remember: mapping out of a sum, or mapping into a product, these two. Then the rest is kind of follows, right? Now there's one more thing, namely mapping out of a product, okay? And I think this is something we'll talk about next time, okay? Mapping out of a product. There is nothing for mapping into a sum. So like if you see something that's a mapping into a sum, well, then you really have to work hard. You have to do some real work other than just drawing these arrows. Okay? So I'll see you in 2 days. Thanks.